Hey, it's Mr. Shrum, and I am back with the mastery test walkthrough for the kinetic and potential energy section. Last time we talked about potential energy and the position and how position of objects within force fields give them energy that can be stored or used for later. And then we have kinetic energy, which is energy of motion. Those are with moving objects. And now we're going to calculate those in these mastery test questions. And starting with number 1, I'll read the question. A bob of mass 0.18 kilograms is released from a height of 45 meters above the ground level. What is the value of the kinetic energy gained by the bob at ground level? Well, if something is dropped, at this height, it has potential energy. And once you release it and it begins to move and accelerate towards the ground, it gains kinetic energy. That potential energy is transformed into kinetic energy. And it wants us to calculate the value of the kinetic energy gained by the bob once it hits the ground. If energy is conserved due to the law of the conservation of energy, all of the potential energy is transformed into the kinetic energy. So we can just calculate the potential energy, and that will give us the amount of energy in the entire system, okay? Because we do not know how fast the object is moving, so we cannot calculate the kinetic energy. But we can calculate the potential energy that it had before it was dropped. And the equation for potential energy is mgh, the mass, which is 0.18 kilograms, times the acceleration due to gravity, which is 9.8 meters per second squared, and the height, which is 45 meters off the ground, right? So mass 0.18 kilograms. That is 45 meters in height. And G is always 9.8 meters per second squared in the questions we're answering in physical science. So if you plug all of that in, that is the answer you get. 0.18 times 9.8 times 45 equals 79 joules of energy. The second question on the teacher walkthrough asks about which statement is true about the law of conservation of energy for an object released from a certain height above the ground. Well, the sum of kinetic energy and potential energy is always constant in the absence of external forces. And in all the questions we're looking at today, this is true. The law of conservation of energy states that the sum of the kinetic energy and potential energy is always constant. Conserved, energy is conserved. I mean, the energy is constant, the same level. Okay. The next question, number 3 on my teacher question list, is talking about a stone. I don't know why I screwed that. That doesn't look neat. There we go. We have a stone. It has a mass of 0.55 kilograms, and it falls to the ground. We know that the kinetic energy at the point of impact is 9.8 joules. What is the stone's velocity at the point of impact? Well, we know the equation for kinetic energy is equal to 1/2 times the mass of the object times the velocity of the object squared. We know the kinetic energy is 9.8 joules. We know the mass is 0.55 kilograms. So we plug that in to the equation. Plug in 9.8 for K, E, 1/2 times M, which is 0.55 kilograms. And you need to solve for V. I scribbled some stuff out, but we're back here. 1/2 times 0.55 kilograms is 0.275 kilograms times V squared. Then you divide both sides by 0.275 kilograms. And then you square root all of that. And if you plug in those numbers into your calculator, 9.8 divided by 0.275, you get V equals 5.97, which is about 6 meters per second. At the point of impact. All right. So really, these are the two equations that you need for this this mastery test section. And then the law of conservation of energy. So total energy is equal to the kinetic energy plus the potential energy. Okay, let's move on. Next question. Jim has a mass of 15 kilograms, and he's running on the ground with a velocity of 2.7. So mass equals 15 kilograms, velocity equals 2.7 meters per second. What is Jim's kinetic energy? So we're going to use that same equation, 1/2 times the mass times velocity squared. And all you need to do is plug in the numbers. 1/2 times 15 kilograms times 2.7 meters per second squared. And that all equals 55 joules. Jim. All right, pretty straightforward. Now, next question, we're dealing with a car. A car with a velocity of 20 meters per second has a kinetic energy equal to 1.8 times 10 to the 5th joules. And remember, 1.8 times 10 to the 5th is just moving the decimal point 5 times to the right. 1, 2, 3, 4, 5. And every time you move it, you're adding a 0. So 1.8 times 10 to the 5th is the same as 180,000 joules. All right. And we need to know the mass of the car. Using this equation, kinetic energy is equal to 1/2 times the mass times velocity squared. Plug in everything we know. We have 1/2, we have the mass, we don't have the mass. We need the mass. So it's 1/2 times m times the velocity. We know the velocity is 20 meters per second squared. And the kinetic energy is 1.8 times 10 to the 5th joules. So we have everything but m. We need to get m alone. So multiply 1/2 times 400. That leaves you with 200. So its mass times 200 is equal to 1.8 times 10 to the 5th. Divide both sides by 200. And that is equal to 900 kilograms. All right, is that making sense to people? And then you would just put that back into scientific notation. In 9.0 times 10 to the 2 is just moving the decimal place 2 times and adding zeros every time you move it to the right. All right. Not too bad. And then we have next question, number 6 on the teacher questions. We have an object of mass 0.1 kilograms or 100 grams, but we'll change it to kilograms for now. And it's dropped from a certain height. It has a velocity of 60 meters per second. If the potential energy of this object is 179.99 joules, how high was the object when it was dropped? So potential energy is equal to the mass times the acceleration due to gravity times the height. And if we plug everything we know in and we solve for h, that will tell us how high it was. So we know the mass is 0.1 kilograms. The acceleration due to gravity is 9.8 meters per second squared. And we don't know h, but we know the potential energy was equal to 179.99 joules. And if you multiply this out, you get 0.98 kilograms times meters divided by seconds squared. And if you divide 179.99 joules by 0.98 kilogram meters per second squared, that will give you h, and that is equal to 183.66 meters, or about 1.8 times 10 to the second meters in scientific notation. So as long as you keep track of the numbers and variables and you're able to plug it in and solve for the number you're looking for, that's all you really need to do. And just be careful with your calculator. 179.99 divided by 0.98. And just keep all of your numbers and double check before you input your answer. Now this question, another car question, it has a kinetic energy of 1.9 times 10 to the third power of joules. If the velocity is decreased, as in velocity is reduced or it goes down, what happens to the kinetic energy? So the one way I like to do this is to just calculate it out for the new V and then look at the old equation to see how it actually changed. If the equation is 1/2 times mass times velocity squared, we can put 1/2 V into this equation. So that's all I'm doing. You see this V, I just make a little parentheses and put in 1/2 times V. 1/2 times the mass times 1/2 V squared. And if you multiply that out, you get 1/2 times the mass times 1/4, because 1/2 squared is 1/4, times V squared. And if you rearrange that, bring this 1/4 out to the front, you have the new kinetic energy, which is 1/4 of the original kinetic energy, right? Because this 1/2 times mass times velocity squared is equal to the original kinetic energy. And now we can plug in the original kinetic energy into this equation. And we know that the original kinetic energy was 1.9 times 10 to the third power. So you can substitute that into this equation now. So now we have the new kinetic energy is equal to 1/4 times the original kinetic energy, 1/2 or 1/4 times 1.9 times 10 to the third power joule. And if you multiply that out, 1/4 times 1.9 times 10 to the third power, you get 475 joules. And in scientific notation, that's 4.7 times 10 to the second power joules. Okay? So whatever happens to the speed, the velocity, because it's squared, that will determine what happens to the kinetic energy. And since you reduce the velocity by half, that velocity is squared in the equation. So 1/2 squared is 1/4 of the original kinetic energy. And if you have more questions about that, be sure to ask me in Canvas. Let me know if I can give you more examples about that. The next question, number 8 on my list, is talking about Anne. Anne releases a stone from a height of 2 meters. She measures the kinetic energy of the stone at 9.8 joules at the exact point of impact on the ground. So the KE equals 9.8 joules once it hits the ground. What is the mass of the stone? Well, we do not know the velocity of the stone, so we have to use the kinetic or we have to use the potential energy because the kinetic energy needs the velocity. And we can use the law of conservation of energy to explain why we can use the potential energy instead. If you hold an object above the ground, it has stored potential energy. And once you release it and it goes towards the ground, that potential energy transforms into kinetic energy. And the kinetic energy, once it hits the ground, is equal to the potential energy at the beginning. So we can use that first equation. The potential energy is equal to the kinetic energy. So we can use the potential energy equation and solve for the mass, m. The potential energy is 9.8 joules. And that's equal to the mass, we don't know that yet, times the acceleration due to gravity, 9.8 meters per second squared, times the height, which was 2 meters. 2 meters. And if you solve for m, so you have 9.8 joules divided by 9.8 meters per second squared and 2 meters, you're left with 1/2 kilograms, or m is equal to 0.5 kilograms. All right. I'll give you one more second to look at all of that. But this is, we use the law of conservation of energy to explain how we know that potential energy is equal to the kinetic energy. The potential energy at the start is equal to the end kinetic energy. And we can use the potential energy because we have the acceleration due to gravity. We know the height, but we don't know the mass yet. And we can solve for the mass that way. All right. 2 more questions. Almost done. And in the next to last question, we are talking about Julie. Julie is cycling. And she's cycling at a speed of 3.4 meters per second. If the combined mass of Julie and the bicycle is 30 kilograms, so m equals 30 kilograms, then what is the kinetic energy? We have m, we have the velocity, and we have this equation for kinetic energy, 1/2 times mass times velocity squared. All you need to do is plug in the numbers, 1/2 times 30 kilograms times 3.4 meters per second, and you square that. You get the kinetic energy, and then you plug it, or you make sure it's in scientific notation. All right. All right. And then lastly, we have number 10 on my teacher questions. Jim is playing with a 1 meter long pendulum, and that is hooked 2 meters above the ground. He lifts the pendulum's bob to a height of 2 meters above the ground and then releases it. Potential energy is assigned 0 value at the ground level. Which statement is true about the problem? Well, if you're raising the pendulum up to a point, at this point, it stops and then begins to change direction. And once it stops, if a pendulum's swinging back and forth, there's a point where it swings and then stops. At that height, the highest position, the kinetic energy is 0, and all of the energy is potential energy. So swing up here, it stops, kinetic energy is 0, all the energy is potential energy, and then it starts moving back this way. At the ground level, that's when it's moving the fastest. So kinetic energy is the max at that point, and the potential energy is 0. And then it moves again up here. It stops again. Kinetic energy is 0. Potential energy is at its max again, and then it cycles back. All right. Potential energy is highest at the points up here as it's swinging back and forth, where the pendulum stops and then changes direction. Kinetic energy is 0. Potential energy is the maximum. And then at this point here, as it swings down, and that point is the fastest. So that's where the kinetic energy is the most, and the potential energy is the least. All right. Okay. I hope that helped you. And yeah, this is another example of the conservation of energy. Energy is not created or destroyed. Energy transforms. So on a pendulum, if you raise it all the way up, potential energy is high, kinetic energy is 0, then it swings down, kinetic energy is max, potential energy is 0 now, and then it goes up again, potential energy is at the max again, and then it stops at the high point, so kinetic energy is 0. But that energy is transforming. Up here, it's potential energy, and then once it starts to move again, it transforms into kinetic energy, and then as it moves back up, the kinetic energy transforms back into potential energy, and then it goes again, back and forth between potential energy and kinetic energy. It's moving, kinetic energy, stops, has potential energy, moves again, kinetic energy, stops again, potential energy. And that is the cycle. All right. Well, I hope this helped you with the mastery tests. And if you have any more questions, email me in Canvas, message me, and I will try to help you as much as possible. And that's all for today. So have a great rest of your day, great rest of your week. Have a nice holiday break, winter break, and I will see you guys later. Bye-bye.